Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hello, my name is Fitrin Rohmawati. I will present a research journal, research by Mary Wagner and Henry Lissaud, and I would like to thank him. This research journal is titled Using Text Math in Math Education and Exploratory Study. We present an analysis of this corpus with respect to the edit behavior and selected linguistic characteristics. Furthermore, we discuss how the collected information can be used to provide support service for the overall authoring process. There are 8 sessions. 1. Introduction. 2. Text marks in a nutshell. 3. Exercise management. 4. Exploratory study. 5. Corpus analysis. 6. Discussion. 7. Completion and outlook. 8. Acknowledgement. Session 1. Introduction. A mathematical assessment system that really supports mathematicians in their daily work has to be highly user-oriented. Our aim is to build document-centric service that support the author in the text editor text marks while preparing a document in a publishable format. Regarding the capabilities of state-of-the-art prop assistant system like Isabelle, Keoki, or Mega, it seems more realistic to provide the authoring assistant to a first-year mathematics student rather than to a mathematician working on the edge of research. Session 2. Text marks in a nutshell. See picture, which is about the architecture of the text mark system. Now, we discuss the architecture of the text mark system, which allow use to manipulate document programmatically. For our purpose, the two most important architectural components are the macroprocessor and the event processor. Once expanded, the rewritten tree is displayed on the current output device by the bytecode. A text mark tree can be displayed in different ways, such as in a Markov language, in the LSE text syntax, or as a chemical expression. One can define a new user input handler and write a text marks add-on to define a new appropriate action to be performed on the current Markov tree in the editor. Such plugins are extensions to event processor and can be written using the scripting language Schemia, which is embedded in text marks. They can also be used to allow external systems such as computer algebra system or prop assistant system to modify the current Markov tree. Session 3. Exercise management. See figure 2. About the architecture of the exercise manager. We therefore decided to use the client-server architecture shown in figure 2, where the internals of text marks are represented by a single combined module called the layout engine. The job of text marks is to display a user interface for navigating through exercise and solution. Using the advanced layout capabilities of text marks, we implement the interface as a plugin that dynamically manipulates documents. Details on these techniques are described in session 3.1. The interface provided are described in subsession 3.2. 3.1. Dynamic document as interface. See Figure 3 about TextMark UI Workout Manager. The question is how to navigate within TextMark to exercise and solution. Our answer can be seen as the equivalent equivalent of Ajax-based browser interface for modern text editor. At Textmarks, we coded the exercise manager menu as a table in a document, using a link object as a button that triggers a plugin interface patient on the server. Sophisticated layout engines are capable of displaying the skin of menus in arbitrary style. 3.2 Automatic versioning of exercise and solution. Because we are interested in consecutive snapshots of a document written in a text editor, we use server-based persistence types for exercise sheet, exercise and solution. Admin user can browse, create, delete, and rename workout sheet and workouts. Standard user can browse through exercise sheet and exercise and create solution. Section 4 Exploratory Study 4.1 Parameters and Workflow. In the first week, we introduced Textmarks to the students who all were completely unfamiliar with LaTeX. The students got quickly familiar with the intuitive usage provided by the WYSIWYG interface of Textmarks, which was a key requirement for being able to conduct this study at all. In the following 10 weeks, the students had to solve and submit 1 out of 4 exercises per week with Textmarks. 4.2 Analysis of the authoring behavior. Using a replay mechanism developed specifically for this study, we were able to analyze student authoring behavior per exercise over time. First, we observed that students spend an average of 30% of their time searching for relevant definition and theorem in the subject matter. Another 30% by generating solution concept on paper, and the last 40% by searching for solution in Textmarks, quite often copy and paste is used to shorten the complex input of a long math formula that differs only slightly from the previous formula. This means that part of the last sentence is deleted, rewritten or corrected, such as adding missing parentheses in a formula. Refactoring operations such as variable rename affect generally more than one sentence. Section 5 Corpus Analysis 5.1 Formula Verbalization. Figures show the formula verbalization grade for every exercise. An exercise is classified as weekly if at least one weekly verbalized formula sentence occurs. The analysis refers that 1. Service for symbolic formula are both development. 2. Being able to fully parse symbolic formula and weekly verbalized formula gives a cover age of at least 70%. 3. A linguistic ontology is required to deal with strongly verbalized formula. 5.2 Style of sentence. The analysis in figure style of sentence show that 1. A linguistic ontology is absolutely necessary to support text style from like the one in the first exercise, because the comparison of less than 50% is not acceptable. 2. For computational proofs with case distinction, the handling of simple connector and weakly verbalized formula gives an excellent coverage of at least 85%. 5.3 Concluding step. Figure concluding steps show the analysis of concluding step which draws the following conclusion. 1. Verbalized concluding step the almost never occur in computational forms. Even symbolic conclusions are very rare. 2. In correlation to the sentence style aspect, we can observe that 50% of the text style forms require a linguistic ontology in order to understand the verbalized concluding step. 5.4 Justification. Figure justification reveals that not supporting verbalized reference result in a medium coverage of the most 65% in the worst case, which might result in a low user acceptance. 2. Different linguistic ontologies are required to effectively understand verbalized reference: a document ontology, an argumentation ontology, and a concept ontology. At least the concept ontology needs to be expanded dynamically. For example, whenever new definition or name local hypotheses are stated. Section 6. Discussion. According to the result of our study, an ideal mathematical existence system should have at least the components shown in figure. 1. Natural language analysis and generalization. Weakly or strongly verbalized sentences have to be analyzed, generalized. We are currently integrating the shallow natural language generation system. 2. Context memory. Natural language has to be generation in adaptation of the style used in the context. 3. Document aspect analysis and dynamic adaptation. Different language phenomena have to be analyzed and put into the context. Notation and reference should be dynamically adapted. We will use the mediator system for incremental parsing and semantic and base refactoring. 4. Theorem proper and four-step generatory analysis. The job of the theorem proper is to verify the correctness of the forms or to generate missing form step and at an appropriate level of generatory. We will use the theorem proper mega as specified foundation. 5. Ontological knowledge. In order to deal with strongly verbalized sentence, we need to build up and dynamically extend different language ontologies. Section 7. Conclusion and outlook. By analyzing the covers collected in the exploratory study with partial mathematics, we were able to identify some desired requirements for the manufacturing support system. The result of the studies carried out are of course specific to the first-year mathematics student. We need to study further to transfer the result and general case. In order to reasonably limit the amount of work that needs to be invested into the second system, we cast a basic domain such as simple set theory. The aim is to evaluate and compare both systems with respect to user acceptance and return on investment. Section 8. Acknowledgement. The authors would like to thank Prof. Dr. Volker John, Mr. Rollins, and their student assistants for the mathematics department of the Saarland University for supporting our study in the first year course Mathematics for Informatiker. This research is supported by the German National Academic Foundation. Thank you.